All right, can you, maybe I'll try the PDF. All right, how's this? Can everybody see and hear me all right? Okay.
What the full screen?
I'm putting the whole screen. Is it, that's not what's showing up? All right, so I was originally planning to participate in person, but then I came down with a fever and a cough. It doesn't seem to be COVID, but I'm here virtually instead. All right, so I want to talk about Cauchy slice holography and the information paradox. So I've given some talks about Cauchy slice holography before, and I thought this time, instead of trying to carefully justify all the details, I'd try to go a little bit further with it and apply it to this puzzle we're all interested in. So this talk is going to be based primarily on two articles. One of them is my paper with my PhD students, Gonzalo and Rifat, on Cauchy slice holography. And they're on the, they're very good students who are on the postdoc market right now. So if you're considering who to hire, they'd be strong choices. And another paper that is not actually out yet about information bottlenecks and the covariant entropy band. All right. Yeah. Sorry, what is that? All right. So one way to express the research goal I'm aiming at here is what you might call the oxymoron of local holography. So, yes.
I don't think the slides are like.
They're not advancing?
Yeah.
Okay.
Yeah, the slides are not advancing.
Okay. Let's try something else then. All right, what about this?
Yeah, that's good. Yeah,
okay, good. So these are my PhD students. All right. So local holography, it almost sounds like a contradiction because the whole point of holography is the state is encoded in the boundary. But on the other hand, to make contact with semi-classical bulk physics and to have a local description of the bulk, we still want a description of holography that is itself more local in the sense that it gives maybe a detailed description of how qubits flow out from the center of the bulk to the boundary and become the CFT state there. So this is the goal of the tensor network program, but as most people here know, this has difficulties accounting for some ADS scales and dynamics. So that motivated us to consider Cauchy slice holography, the idea of which is that there exists field theory, T-squared deformed field theory, that has the property that its partition function gives a wave function of a quantum gravity state with an emergent time dimension. So you have on the left here, Z, the partition function, that is a function of a metric and some other sources. I want to interpret this as like it's a fixed quantum field theory background sources. When I say fixed, I don't mean you can't vary them, but I mean they're not automatically varied in the path integral. They're independent variables. So on the other hand side, you have the same metric, scalar, etc. here, but now you interpret them as spatial configuration variables, and you think of them as defining a Wheeler-DeWitt state satisfying the constraint equations of quantum gravity. So this is the fundamental equation of the duality. Whenever you have a partition function, the obvious thing to do is to start differentiating with respect to the various sources. And it has a different interpretation on both sides. If you differentiate on the partition function side with respect to the metric, we would call that the stress energy tensor. On the other hand, if you differentiate with respect to the spatial metric, we would call that the idiom momentum. So these things are going to be numerically identical to each other as derivatives, but they mean a different thing on the two sides of the duality. And the same thing would apply to differentiating with the spec to some scalar source, which would give you some operator on the field theory side, and the canonically conjugate momentum to the scalar field on the other side. By construction, it turns out that the t-squared theory satisfies the Wheeler-DeWitt constraint equations automatically. So this formalism, unlike tensor network models, actually automatically includes gravitational dynamics. There's a sense in which you can't get rid of it even if you wanted to. So that seems like a useful feature. And since it's defined in the continuum, at least at the present stage of construction, it seems we'll get some ADS scales as well, although there may be difficulties when you go all the way down to the Planck scale. Now, in cases where the Cauchy slice that this partition function is defined on is open, i.e. there's a codimension 2 boundary that's like a Cauchy slice, for example, a boundary CFT, it's also necessary to specify a state at the boundary. So this is the usual way things work with partition functions. If you have a closed partition function, you just get a number. But if you have an open partition function and you need to specify boundary conditions at one end, then you get a state at that end. It turns out that in the asymptotically ADS case, the states you need to specify at the boundary of infinity of the Cauchy slice is actually the same as the states in the usual ADS CFT. So that means that the two theories can actually interface at this junction between them, and you can evolve from the Cauchy slice and then along the Lorentzian boundary. Now, this is good because it means that you can use Cauchy slice holography to construct explicit, if you calculate these partition functions, explicit maps from bulk states to boundary states and boundary states to bulk states. Now, things are a lot more confusing in the case of a closed universe where the partition function just gives us a single number, which would take the form of a single allowed Wheeler-DeWitt state, like specifying a particular wave function of the universe. It's confusing because a lot of how we think about physics normally, we can't do when our Hilbert space is one-dimensional. At least naively, since a closed universe has no spatial boundary, you might think that holography would imply that it's dual to a trivial Hilbert space, but it's harder to interpret. It does, however, seem to agree with this respect with what the way people usually think about the DSCFT conjecture, where Scri plus is related to the partition function of field theory. This would differ in that it's at finite time instead of infinite time. So I'm going to leave aside the DS CFT case, or the DS Cauchy slice case for the moment, and we'll just consider the ADS case for now. So for quantum gravity vacua with lambda less than 0, you can obtain the Cauchy slice holography theory by starting with an example of ADS CFT and deforming its Lagrangian by a specific irrelevant deformation that is known as the T-squared deformation. The reason it's called that is that the deformation is quadratic in the stress energy tensor. And in fact, it's designed so that the terms that are quadratic in the stress tensor look like the kinetic terms of the ADM momentum. I suppose it's possible I got the overall sign wrong here, but the relative sign is certainly correct, where D is the boundary dimension. Then you also need to add some curvature terms, the details of which depend on the dimension, and you need to add some matter terms, the details of which depend on the particular matter that is in your bulk Hamiltonian constraint that you want your partition function to agree with, which presumably should be the same as whatever bulk Hamiltonian constraint the CFT you started with is dual to. Now, the details of this are in our paper quite generally, but for some specific cases, this was constructed by Hartman, Kruzoff, Shagelin, and Gini, and also by Marika Taylor. Now, I've written this as a differential equation here. You can also write it as a path over an exponential acting on the partition function. It means the same thing. But the point is, to get the Cauchy slice theory, you need to take mu to be a finite value. And because of that, it's important that this deformation has to be integrated from mu equals 0 to mu equals finite. And when you do that, since this definition of the stress tensor is itself implicitly a function of mu, it's important at each stage of this deformation to use the stress tensor from where you're at in this flow. Now, since mu is the only dimensional parameter, its value doesn't actually matter. That is, if you and I pick two different finite values of mu with the holographic sign, and then our results will be the same as each other up to a length rescaling, since mu is the only dimensional parameter. Now, because deformation is irrelevant, which a field theorist would say that is usually non-renormalizable, for the usual reasons we might worry that this theory is ill-defined, and that indeed we believe that generally speaking, it's going to require some sort of UV completion if you want to make sense of it near the Planck scale. That's not too surprising. But in the holographic regime of n equals infinity, and probably we argue in our paper in a 1/n expansion, the spectrum of the theory is solvable, and at least in this regime, the theory seems to be well defined. Now, if you look at the spectrum on the cylinder, there's a rather strange phenomenon that appears. At a certain point, there's a branch cut, and the energy eigenvalues become imaginary rather than real. So the theory is not unitary. Now, when I say it's not unitary, since I'm about to mention we're about to discuss the black hole information puzzle, it's important to keep separate two very distinct notions of unitarity. In Hawking's calculation, the kind of non-unitarity that appeared was pure states evolving to mixed states. This is not the kind of non-unitarity that we're discussing here. Here, we are discussing that there is no positive definite norm that is preserved by real, that is Lorentzian signature time dynamics in this theory. Now, since we're evaluating this thing on Cauchy slices, perhaps we're actually taking it as a Euclidean signature theory. So the significance of this might not be immediately obviously problematic, but it does mean that the nicest norm to put on states is not positive definite. Now, this was inevitable, as if you look at Wheeler-DeWitt states of, for example, the Hartle-Hawking state in vacuum ADS, it's just a true fact that this state does not obey reflection positivity if you interpret it as a partition function. So, and this is also type of non-unitarity is also familiar from DSCFT. So I think we have to learn to live with it and somehow figure out how to extract positive probabilities at the end of the day. In fact, one thing you should not do is just throw away these imaginary energy eigenvalues, because it turns out they're actually crucial for obtaining the correct physics in the Lorentzian signature higher dimensional theory, when your Cauchy slice is embedded in a way that in your bulk that makes the ADM momentum real and non-zero. That is, the extrinsic curvature is real in the natural way of defining it in a Lorentzian signature theory, then that corresponds to an imaginary stress tensor, which is not something you could have in a unitary theory. Okay, so to show you what the spectrum looks like, the original CFT spectrum, whose energy I'm describing by this curly E, has a ground state, has some sparse spectrum of states at low energies, and then at a certain point you get a bunch of black holes, and it's still a discrete spectrum, but very, very closely spaced. Now, when you consider the T-squared deformed, when you consider the T-squared deformed spectrum, the energy eigenvalues become complex. The way it works is that at a certain point, you take a right, there's a square root in the formula for the spectrum. At a certain point, you go at 90 degrees off in both directions. In order to keep things behaving in the without breaking time reversal explicitly and without the energy eigenvalues behaving discontinuously, I believe it's probably necessary to think of this theory as having states corresponding to both sides of the square root, which means that the spectrum is shaping across. So there's 4 branches, and positive probabilities arise, I think, if you confine attention to just one branch, then I think you can identify a norm that is positive definite on that branch. So this seems to indicate that as long as the boundary of your space-time region has a space-like extrinsic curvature of fixed sign, that you still have a positive definite Hilbert space associated with that region. This may be why entanglement wedge reconstruction occurs. That is why something goes wrong if you try to reconstruct past the extremal surface, which is where the spatial extrinsic curvature goes to 0. But that's just speculation at this point. Okay. Now, because the T-squared deformed theory has a well-defined spectrum, it's also possible to calculate the density of states at a given value of the energy on the cylinder. And applying the duality dictionary, one finds that this microcanonical entropy S is actually exactly equal to the Bekenstein-Hawking entropy if you're sitting right at the branch point. That is A over 4G. But it's bigger or smaller at other values of E. So it's smaller if you're on the real axis, and it's bigger if you're on the imaginary axis. More generally, it's also possible to calculate the microcanonical entropy on a section sigma of a non-stationary tube, i.e. a Cauchy slice of ADS, which might be a cylinder of variable radius. In that case, one finds that the entropy S only depends on codimension 2, that should read data, and that S equals A over 4G for a broad class of marginally trapped surfaces. So in the general dynamical setting, it seems that marginally trapped surfaces are what live on this branch point. Now, the significance of this is that this microcanonical entropy bounds the total amount of information that can flow from the left to the right through sigma. So here's just the same picture I was saying before. The marginally trapped surfaces with null extrinsic curvature have exactly A over 4G. Well, I just said it, so I'm going to move on. All right, now let's discuss how this is potentially relevant to the information paradox. I've drawn here the Penrose diagram of a black hole that has formed from collapse and starts evaporating. One way to express the information paradox is it involves a tension between two different viewpoints. In one tension, we go to the CFT, and we know that the CFT is unitary. So information cannot be lost from the perspective of somebody who measures boundary observables. On the other hand, in the bulk semi-classical perspective, you can construct what's called a nice slice, shown here in green, where although one naively expects semi-classical physics to be valid, nevertheless, the infalling matter, shown in purple, the Hawking quanta outside the horizon, and the partner modes all lie on the same slice. And so it seems that if the information of the infalling matter comes out in the Hawking radiation, that we violated the no cloning theorem. Now, the advantage of Cauchy slice holography is instead of asking how is this CFT thing related to the nice slice picture, we can actually do holography on the nice slice itself. So that means that we, instead of comparing apples to oranges, we could be looking in more detail at exactly what's going on with the Hawking radiation and the partner modes without them having to go all the way out to infinity. So here's a picture of the Cauchy slice. So originally, the black hole forms a collapse, and there's some infalling matter involved. Then we evolve up to some late time, at which point we choose for the Cauchy slice to go out to infinity. And so we have a period of gradual evaporation, and then at a certain point, based on what time we've chosen to look at, the area of the Cauchy slice diverges and goes off to infinity because it's exited this black hole region. So that's shown over here. The Hawking radiation is over here, outside the black hole, and the partner modes are inside. Now, thinking of this as a partition function, we can also think of it as a story where we evolve the theory with some boundary condition on the left that is pure on the left, and then we evolve to the right, and we ultimately, after evolving through this entire Cauchy slice, we end up with a state on the boundary, and that should be the state of the CFT. That is dual to the Cauchy slice with that particular thing going on. Now, the infalling matter and the Hawking partner modes show up in this picture as sources in the partition function Z on the Cauchy slice. Now, several comments about this. The first comment is so long as the sources on the Cauchy slice are all pure, the dual CFT state on the boundary is manifestly pure as well, since after specifying all boundary data, and the boundary data is just on the right here, the Z is just a number. Now, you could get a mixed boundary state if, for example, the infalling boundary is mixed, but that isn't surprising. Everybody believes it's mixed if you start with a mixed state. So let's assume, for the sake of this analysis, that the black hole starts in a pure state instead. Now, so long as the sources of the Cauchy slice are all pure, I said that the boundary state will be pure. But now the second point I want to make is that actually taken as a whole, these sources are pure. So we've assumed the infalling matter is pure. The partner modes and the Hawking modes are individually mixed, but they're entangled with each other. The whole point of the partner modes is that they purify the Hawking radiation. That purity can be represented morally by drawing some tensor network lines between the partner quanta and the Hawking quanta that sort of allows an additional channel for information to come through. So taking everything into account, you still expect a pure state on the boundary. Now, essentially the same story obtains if we pick instead an arbitrary surface sigma at some point during the evaporation process. But now, instead of the Hawking modes and partners, we should instead consider the field theory entanglement of the thermal atmosphere across sigma. So that just changes where the entanglement is located. We're now thinking about the entanglement near sigma on one side and on the other side. Now, if the nice slice happens to be foliated by marginally chopped surfaces, then the classical entropy is given, as I said, by A over 4G. And because of the extra tensor network lines, the maximum information flow across sigma is presumably given by the generalized entropy. So that would be the sum of the area of sigma and the capacity of these lines. So that should be the generalized entropy, A over 4G plus Sn. This is like an information bottleneck. A maximum amount of information flow allowed given the specified area and extrinsic curvature. Now, we aren't forced to consider marginally chopped surfaces. You could actually consider whatever Cauchy slice you like. But if the slice is not foliated by marginally chopped surface, it turns out that the bound on the entropy is much more complicated. So that's the sense in which the apparent horizons are nicer. Now consider just the sources on the left of the slice sigma. If you calculate the semi-classical entropy of the QFT modes, this is probably a bit confusing because I think I changed my terminology here. Let me just say the right thing here. So if you have some infalling matter come across here, which for purposes of this slide might actually be in a pure state or a mixed state, then the generalized second law is actually going to tell you that the generalized entropy of the black hole is increasing with time. And because the generalized entropy of the black hole is increasing with time, you're actually always going to satisfy this bound. So it appears at first that nature is trying to protect us from actually having a problem with the information bottleneck. But this is actually not true. The key issue is that we actually have to decide whether we want to think of the Hawking pairs as being physical qubits, that is part of the apparatus used to transmit the message, or logical qubits, i.e. part of the message that we are trying to recover. While we can view things either way, we need to be consistent in any given calculation of bounds, since the use of the tensor network lines to send a message from the left-hand side to the right-hand side uses up the qubits in question. If we take the alternative picture and we consider these partner modes to be things that we're trying to reconstruct at sigma or out at infinity, then we can no longer use them to transmit information to the other side. And in that case, a different inequality becomes relevant. We would have a problem with this information bound if the entanglement entropy is less than the A over 4G of this surface sigma. Now, this inequality is violated after the page time, but purity is not violated. So it seems to me the only possible scenario, if there's not enough states on sigma to capture all of the possible semi-classical descriptions to the left of sigma, it must be that there's post-selection, i.e. that Z maps multiple bulk states to the same boundary state. I should say this formula looks rather strange for those used to how generalized entropy works. I'm presupposing here that one is taking the UV cutoff of the field theory entropy to be much larger than the Planck scale. The UV cutoff is relevant because I'm assuming that we treat modes that are below the UV cutoff as physical qubits rather than as logical qubits. So in that sense, it's a UV cutoff dependent description. If you instead looked at modes going all the way to the Planck scale, it looks like you could actually argue that post-selection maybe occurs almost immediately after the black hole evaporates any amount of time at all. So that might be not having to wait for the page time to see something interesting happen seems like a feature, but then you have to go to the Planck scale. All right, the conclusion here is somewhat morally similar to the Python's lunch idea, but with a more explicit holographic model of what's going on in the bulk. Entropy bounds restrict the total amount of info behind a bottleneck surface, but in a way that's difficult to detect with simple measurements. Now, in this talk, I haven't tried to make any specific connection to gate complexity, but rather I just mean that you don't run into post-selection problems unless you try to measure lots of partner modes, or at the same time as you measure some partner modes, measure lots of infalling matter that's in an entropic state. It also feels somewhat similar in flavor to the Horowitz-Maldacena final state proposal, except here the post-selection can be calculated on an arbitrarily nice slice. So you can pick the Cauchy slice to be wherever you like, and it has nothing especially specific to do with the singularity. Also seems to connect to Ying Zhao's idea that tensor networks are best defined using trapping horizons. And by work with Netta Engelhardt, the A over 4G seems like a coarse-grained entropy for marginally trapped surfaces, but not for other surfaces. I should really have also mentioned the work by people at Berkeley, the Sanchez and Weinberg and Nemera on the holographic screens as a model of holography. All right. So that is all I had to say, but I'm open to questions.
Questions?
Hi, Aron. You defined a state on the bulk Cauchy slice using a t-squared deformed theory, and I just wondered if you could explain why that state that you constructed solves the Hamiltonian constraint.
Right. So that's right. It's basically because you start with a CFT that satisfies an equation like trace of the stress tensor equals 0 in odd dimensions or the conformal anomaly in even dimensions. So the CFT obeys an equation like that. Then when you deform by this irrelevant operator, the right deformation to use is basically whatever it needs to be, so that when you commute this equation past all that stuff, it mutates into the Hamiltonian constraint. So CFTs obey two key relations with their stress tensor. They have stress tensor conservation, which actually takes the exact same form as the momentum constraint of GR. And then it also obeys trace condition, and it's the trace condition that deforms into the Hamiltonian constraint condition.
Okay, thank you.
I don't know, how do you still recover unitarity if you have a post-selection on the Cauchy on a nice slice?
It's a good question.
Non-unitary.
Right, but we're talking about not at that point, we're talking about non-unitarity in the sense of if you start on the left and evolve to the right, and then you get a CFT state. So that evolution is not unitary, but that's compatible with evolution on the CFT side at spatial infinity being unitary. So you can think of Cauchy slices as, I mean, usually we think of Euclidean path integrals as just a prescription for giving us a state. So the Cauchy slice theory is like a prescription for giving us a state. And the fact that it's, as we showed in our paper, it seems compatible with CFT evolution. So the fact that the CFT is unitary still requires the bulk evolution to be unitary. But I think the bulk evolution you're interested in for those purposes is not evolving from left to right on this Cauchy slice. It's evolving in time from one Cauchy slice to another Cauchy slice. So I think it's sort of two different notions of unitarity. But it's quite a subtle issue. In our paper, we discuss multiple different notions of unitarity that this theory possesses and some that it does not possess. So I hope that helps.
Hi, Aaron. I had maybe a version of Jonathan's question from the quantum complexity perspective. So it's known that when you do post-selection in general, you can often supercharge the computational power of quantum computing to unphysical levels. So I was wondering if you have any thoughts on whether the post-selection that you need to use in this procedure avoids that problem?
I mean, I think it probably should not avoid it entirely, in the sense that I think it should be the case that you could replicate, for example, the Python's lunch scenario in the Cauchy slice theory, where you have a bottleneck and then like some bag of gold behind it or something. And it should be possible, I think, for that to be dual to something pretty complex. I mean, presumably you can't exceed whatever you could do on the CFT if you just have the CFT on the boundary. But if you're just talking about this particular Cauchy slice theory with some complicated bag of gold, what does it correspond to on the boundary? I think there's no reason why that might not be might not lead to a complex state.
Maybe I'll just comment on that. So I can't quite tell, but to what extent what you're saying is similar to the non-isometric code that Netta mentioned in her talk. But at least in that story, which also involves post-selection, there was a recent paper by Preskel and Kim arguing that you don't get any computational speed up from the post-selection, which is in the map. That's just a comment.
Dan, can you say in what context you don't get speed up? Like if you're trying to do what?
Well,
maybe I can just briefly comment.
Oh, is Isaac here? Okay, yeah.
Yeah, so
Yeah,
basically, yeah, in that setup, you like whatever you can do using your normal quantum computer, it doesn't really give you, like, even if you use a black hole, it doesn't really give you any speed up, at least within that model. This is something So even though there is post-selection in the model, it's post-selected on a particular state, and that somehow prevents you from getting any kind of speed up.
All right, well, this is not something I've personally thought about carefully, so you should probably trust these other guys. So,
Aron, is there some condition on the Cauchy slice I pick? Because I mean, it seems like I could choose some Cauchy slice that from the bulk point of view is perfectly good Cauchy slice, but it has, you know, maybe some wiggles in the time direction. So it has all kinds of minimal surfaces on it that are, you know, that have nothing to do with any physics. So yeah, is there some condition on the Cauchy slice?
no, I mean, because I mean the wheeling to width state, the wheeling to width state satisfies the Hamiltonian constraint equation, which means morally speaking, it is a superposition of all possible Cauchy slices. Now, the way this actually works is if you're mapping from the bulk to the boundary, you can pick specific metric data on your Cauchy slice, and then you get a particular CFT state. But if you're mapping from the CFT back to the bulk, then you get a quantum superposition of all possible times. So these very wiggly slices should be part of this story, but there's a serious caveat here, which is a lot of my strong claims here about marginally trapped surfaces and A over 4G. I should level with you guys and say so far I've only really worked it out in the spherically symmetric case. So
Yeah, I mean,
think
it seems like
more generally, but
yeah, you could pick a slice that has like some tiny bottleneck or something, and it would, you know, that's whose area actually has nothing to do with the entropy.
right. But the point is, if it's not a marginally trapped surface, the bottleneck is not given by the area; it's given by some other formula. That's how you evade these counterexamples.
I don't understand how that formula can give you the correct answer, which I think you want to be the area of the extremal surface, right? In more general settings than what you considered. In particular, if there's stuff falling into the black hole, for example, that decouples the areas inside the black hole from the areas of some extremal surface you might have had earlier. I mean, how can you do this just with local data?
I'm not sure I understand the question. Can you rephrase?
How in a general spacetime where you can't rely on analyticity or something, how can you hope to recover from local data the information that you want about the area of the extremal surface?
Oh, I mean, I think it's going to be a very complicated formula in general, but I believe the microcanonical entropy of this T-squared theory is going to turn out to be determined by the area of the extremal surface of the space-time, and sometimes that's very difficult to calculate, but it's going to be equal to that. That's what I believe is true. But for a marginally trapped surface, my construction data shows it just as equal.
By complex, you mean that it's not computed from just local data on the codimension 2 surface.
It's not a local integral in general. It should depend only on codimension 2 data, I think, but in a way that is non-local along the codimension 2 surface. That's what I believe is true.
I don't understand how that's consistent with my ability to throw shells into the black hole and things like that just disconnect the area. And I mean, that give me a way to make the area of the quantum extremal surface independent of the local data on the surface you're looking at.
Well, don't forget that these bounds depend on the energy as well as the metric. So so there's some dependence on extrinsic curvature here. There's dependence on operators as well as on sources from the field theory side. So you can't it depends on restricting to a specific class of quantum states who have certain whose observables like the energy take certain values. So, or more generally, the stress tensor. So it could be a general, if you throw across a cell, that should probably change the entropy.
No, it could be an impure state.
Yeah.
Okay, let's thank Aron again.